Okay, I don't see anybody logging on yet, but we will go ahead and get started at about 9:15. This is our last. Um, okay, it's 9:15. So this is our last lecture, last Blackboard Collaborate video. And if anybody logs in, I'll say hi to them, or that they can watch the video to get anything they missed. But anyway, so this is the last thing we're going to talk about, the normal distribution. Now, online, you do have a test 4 and a final. You can take test 4, the final exam, however, you need a password for, and you can get that password from Miss Creech or Mr. Wright. Excuse me. I haven't given them the password yet, so I'll try to email them this week and let them know what it is. But let's talk about the normal distribution. Now, we've been talking about distributions, but just to review, when we talk about a distribution, we're talking about a set of data points. We're talking about how many times each distinct data point occurs. So a normal distribution is a common distribution in statistics. Many data sets fit into either exactly or approximately a normal distribution. This is good because normal distributions are relatively easy to work with. Some characteristics of the normal distribution are it's bell-shaped, symmetric, and only has one mode. And in fact, the mean, median, and mode of a normal distribution are the same. If you're using a normal distribution because your data approximately fits that, the mean, median, mode may not be exactly the same, but they will be close. And the total area under the curve of a normal distribution is 1, or 100%. So this is what the normal distribution looks like. Now remember, it's bell-shaped. We had a histogram, actually, that we called bell-shaped, and we said that most of the data points in that histogram were close to a middle data point. And remember, I said we'd talk more about that later. Well, that middle data point is the mean. So if you have a histogram and you have a bell-shaped curve, or the histogram is bell-shaped, then you probably have a normal distribution. You could even picture us drawing a histogram that fits this data, right? So think about this curve as if I had a histogram, then I could just draw this curve over the tops of the histogram, and that would provide the normal curve for the normal distribution. All right. Excuse me. So what we have in the normal distribution is we usually have one standard deviation above and below the mean, two standard deviations above and below the mean, and three standard deviations above and below the mean labeled, and that's because of something called the empirical rule. In a normal distribution, 68% of the data falls within one standard deviation of the mean. So basically, 68% of the data, or over half the data, will fall within one standard deviation of the mean in this area. 95% of the data falls within 2 standard deviations from the mean, and almost all the data, 97 or 99.7% of the data, falls within 3 standard deviations of the mean. Sometimes this is called the 68, 95, 99.7 rule, so that you can remember the percentages, but it's also called or known as the empirical rule. So let's say that we know that the data set that we're looking at or working with approximates the normal distribution, or is distributed normally. There are a few things, or there are some decisions we can make, or some analysis we can do based on the empirical rule. So that's what we're going to talk about next. Well, I'm wanting to go to the next slide here. It's not letting me. Okay, well. Okay, here we go. Sorry about that. All right, let's look at this figure. It says the figure illustrates a normal distribution for the prices paid for a particular model of a new car. The mean is $12,000 and the standard deviation is $5,000. Use the 68, 95, 99.7 rule to find the percentage of buyers who paid between $10,500 and $12,000. Alright, so here what I have is, in the middle I have the mean, and the way that this works basically is that I have one standard deviation below the mean, so that means I subtract 500, which is a standard deviation, from the mean, and I add 500 to the mean. So one standard deviation below the mean is 11,500. One standard deviation above the mean is 12,500. Then to get 2 standard deviations, I just subtract the standard deviation of 500 times 2 from the mean, and to get 3 standard deviations above and below, I subtract and add 500 times 3, right? So that's how I got these figures here. So what I want to know is, I want to know the percentage of buyers who paid between $10,500, so this is $10,500, and $12,000. So I want to know the percentage of buyers that fall within this block here. Well, I know that well, I need to use 2 things here, I guess. The first is I need to use the fact that let's do this in a different color here. Do this in green. I need to use the fact that the mean divides this distribution into 2 equal halves. So if the whole thing is 100% or 1, then on this side it's 0.5. And on this side it's 0.5. Now, I know that from here to here will be 99.7% of the data, or 0.997 as a decimal. But I don't want everything. I just want everything on this side. So what I'm going to do is I'm going to divide 99.7 or 0.997 by 2. And I get 0.4985. And actually, now that I think about it, while this is true, this is 0.5 and this is 0.5, I don't really need that information because all I needed to do, since this was from the mean over to 3 standard deviations, was take this 99.7 and divide by 3. So this 0.5 and 0.5 is true. We may use that later. But in this case, the only thing I needed to do was recognize that this was 1/2 of the 99.7%, because it was just from the mean to 3 standard deviations below the mean, not 3 standard deviations below to 3 standard deviations above. So this is it. What is the percentage of people who paid between $10,500 and $12,000? Well, it is 49.85%. All right, what percentage of buyers paid between $11,500 and $12,500 for a new car of this model? I'm going to go ahead and clear so that I can have a clear diagram. So here I have 11,500. Uh-oh. And 12,500. Well, you know what? That is basically just 68%, right? Because it's 1 standard deviation below the mean to 1 standard deviation above the mean. So it's just 68%. There's no other calculating I have to do. All right, let's look at this one. He says, what percentage of buyers paid between $11,000 and $12,500? So I'm going to clear. So 11,000 right here and 12,500. Well, so I know that from here to here will be 1/2 of 95%. And then I know from here to here will be 1/2 of 68%. So basically I'm going to take half of 0.95 and add that to half of 0.68. So 0.95 divided by 2, that's 0.475. At 0.68 divided by 2 is 0.34. Thought I heard something. So that basically is going to be 0.815 . Draw my calculator. So 0.815 or 81.5%. And this actually goes down here. Sorry about that. All right, last one. It says, what percentage of buyers paid more than $12,500 for a new car of this model? So I want to know more than $12,500. So here's $12,500, right? And here's where I'm going to use the part about 0.5. So basically this whole side is 0.5. But I want more than that. So I want from here over. So all I have to do, if this whole side is 0.5, is subtract this part right here, and then I'll have what's left over here. So I'm in luck because I know that from the mean over is basically over to 12,500 is half of 68% of the data. So 0.68 divided by 2 is 0.34. So this is going to be 0.5 minus 0.34. So that's 0.16. So basically 16% of buyers paid more than 12,500. All right. Let's talk about a couple more things. It says, because data sets have different means and standard deviations, to compare two sets of data, we often standardize the data points using a value called a z-score. Usually the value before you standardize it is called a raw score. And so the reason why we do this is that z-scores can help us compare things that are basically different. If you have one set of data and you look at another set of data, and they have different standard deviations and different means, then it's really hard to compare those two. What if those two were people who take the ACT in two states, for example, or people who take the ACT versus people who take the SAT? How can we compare those two tests? Well, you can't unless you can find some way to standardize those scores so that they can be placed on the same distribution. And a z-score is one way to do that. A z-score can be thought of as the number of standard deviations that a data value is from the mean. When you have data expressed as z-scores, the mean is always 0 and the standard deviation is always 1. So the normal distribution in terms of z-scores will look like this. 0 is always in the middle, and standard deviation is always 1. And we can use the following formula to convert from what we call a raw data value to a z-score. You take your data value, subtract the mean from it, and divide by the standard deviation. All right, so it says the heights of Canadian women are normally distributed with a mean of 159.5 centimeters and a standard deviation of 7.1 centimeters. Find the score for the following pieces of data, the z-score. So what if there was someone who was 148.2 centimeters tall? Well, let's find the z-score. So z is going to equal Let me get rid of this for a minute here. I don't know what I was doing. So z equals 148.2 minus 159.5 divided by 7.1. So 148.2 minus 159.5 divided by 7.1. So this z-score is negative 0.224162, but generally we let z-scores just be 2 decimal places after the decimal point. So I'm going to say that z-score is negative 0.22. Wait a minute, let's see. 140, let me see, I think I may have gotten my calculator mixed up. Okay, let's see, 148.2 minus 159.5 divided by 0.7, or 7.1. Yeah, for some reason, this is totally wrong. Sorry about that. For some reason I looked at the wrong number on my calculator, or did something with my calculator, because I thought that was a little bit odd, because this is really negative 1.59. Okay, what about a height of 160.3? All right, let's see. Well, 160.3 that's going to be 160.3 minus 159.5 divided by 7.1. So 160.3 minus 159.5 divided by 7.1. And so for this one I got 0.11. I actually got 0.112676, but we'll just say 0.11. All right. It said intelligence quotas on 2 different tests are normally distributed. Test A has a mean of 100 and a standard deviation of 15. and test B has a mean of 100 and a standard deviation of 18. It says use the z-scores to determine which person has the higher IQ. Alright, so if Megan scored a 126 on test A and Patrick scored a 134 on test B, well, I can't compare these yet because they have two different standard deviations. So I need to change these both to z-scores. So Megan's z-score will be 126 minus 100 divided by 15 and that's going to give me 1.73. Patrick got 134 minus 100 over 18. So when we do that, I get 1.88 or 1.88888888. So I'm going to say 1.89. So clearly now we can see that Patrick has the higher IQ. Okay, let's look at the last few problems that I have here. And I have three problems that ask us to look at the normal distribution in terms of z-scores and find the percentage of area or the percentage of data points under the standard normal curve that is specified. Alright, so in order to do this, we're going to need to use a table, or we could use like something like Excel or something like that, but I think a table is just easiest for the problems that we're going to look at. So I'll show you that table in a minute, but let's look at this first one. It says use a standard normal distribution table to find the percentage of area under the standard normal curve that is specified. We want to find below a z-score of negative 148. So if I draw a normal distribution, here's the mean, or 0. That means that negative 148 is somewhere over here. So what I want to do is I want to find the area, or I want to find the number of data values that's below this, so I want to find the data values here. Okay, so I know that I know that this whole side, one side of it is 0.5. So all I have to do is find the data value or the area from here over. Then I can take that area, which usually we let the area use alpha. We let the area be represented by alpha. I can subtract that area and I'll get the area that I need. So here's where the table comes in. So I'm going to stop sharing this and I'm going to start sharing the distribution table. Okay, so notice here that we have a list of z-scores and the area associated with those z-scores. So the table only gives us positive z-scores, but the negative z-scores are the same, right? So the z-score or the area for each z-score will be the area from the mean over to the z-score. So from the mean over if it's positive, over this way, for the mean over this way if it's negative, right? So the z-score we had was what? Negative 148. So let me see here. I'm on page 2 now. Here I have 148. So that area is going to be 0.431. Okay, let's go back to I'm going to write this down real quickly. So what I found, let me redraw this here. So I want to find this area right here. Not this. So I know, based on the table, that from here over is 0.431. So all I have to do is take that and subtract it from this entire side, which I know is 0.5, to get the z-score or the area or number of data values below. So I'm going to take 0.5 and subtract 0.431, and I get 0.069 or 6.9%. So 6.9% of the data values are below negative 1.48. All right, let's do the exact same thing with this one. It says use the standard normal distribution table to find the percentage of area above the standard normal curve that is specified. So that's 1.53. So I'm gonna, before I draw anything, I'm gonna go over here and find this area. So 1.53 I need to go to the second page here. Okay, here we go. .53 is 4.37. Okay, so I'm gonna go back. I already forgot what it was. I think it was 4.37. 0.437. Let me go ahead and pull up yeah, 0.437. Alright, so now in the standard normal distribution, 1.53 is somewhere over here. I want to look at the area that's above, so I want this area right here. So this whole side is 0.5. So I need to take 0.5 and subtract from it the area from here to here, which I just found out was 0.437. So when I take 0.5 and subtract 0.437, I get 0.063 or 6.3%. Alright, let's look at the last one. So the last one is 1.3 and 0.75. So basically what I want is I want to find, let's see, here is negative 1.3 and here is negative 0.75. Now, what I want in this case is I want the area in between these numbers. So what I'm going to do is I'm going to find the area from here all the way over, so the area of 1.3, and then I'm going to subtract the area of 0.75. So I'm going to find the area of 1.3 and subtract the area of 0.75. So 1.3 and 0.75. Let's go back to the normal distribution table. .75 here is 0.273, and 1.3 will be 1.30. That's 0.403. Now I'm just going to redraw this here. So what I want is, this is 1.3. That's 0.75. So now I want only this area. So I'm going to take this whole area all the way over to 1.3, which was 0.403. And from that, I'm going to subtract the smaller area all the way over to 0.75, which is 0.273. All right. So 0.403 minus 0.273, and that's 13.13 or 13%. All right. Well, we're a little early today, but that's it. You should have this document in My Open Math if when you need to use it. You should look at the last homework assignment and the study guide for the final. Take test 4, take the final exam, and I'm working on grades, and I'll try to get your grades out to you as soon as possible. You have the rest of this week and next week to finish everything up, and then and then we'll be done. So I think it's been a great semester. I've enjoyed coming out to the schools and meeting you all. Um, and if you ever need any help with math or any kind of math in the future, you know where to find me, and I'll be glad to help. We'll be here. I mean, we'll be talking more. I'm sure you'll be getting emails from me, and but I just want to take this opportunity to say that this has been a good class. I've actually enjoyed the Blackboard Collaborate. I hope these videos have been helping you, and I hope that the My Open Math homework site, you found it easy to use and helpful as you worked through homework problems. I wish you all the best, and let's just get the rest of the semester finished up so that we can go off and have a good summer. All right, I will talk to you all later.